Good day, everyone. I am Engineer Ricky J. Gomez, and I will be presenting my work titled Gaussian Process Regression, the GPR model development for predicting the PMFC performance against temporal hydrogen crossover in MATLAB. This is published in Journal of Fluid Flow, Heat and Mass Transfer, year 2024. I am with Dr. Dalia Apodaca and Dr. Michelle Andrella in this work. But before I proceed, so I just want to extend my special thanks to the Department of Science and Technology for the NICER grants for this project given to the Mapua University with Dr. Dalia Apodaca as our project leader, to the OSA Assured as monitoring agency, and to Mapua Center for Advanced Materials for Clean Energy Technologies, PMSC research team for the assistance support. So as a background, so issues such as the loss in the overall fuel cell performance, membrane and components degradation, and safety-related problems are some of the direct outcomes of the unintended diffusion of hydrogen gas from the anode to the cathode side. Thereby, they are collectively addressed through establishing a solid understanding about its mechanism and the extent of the implications of such phenomena to the overall fuel cell performance. But before that, I just want to share about what's happening inside a fuel cell, a proton exchange membrane fuel cell. On a high level, hydrogen and oxygen reach electrode surfaces where HOR or hydrogen oxidation reaction and ORR or oxygen reduction reaction occurs respectively, where protons pass through the membrane while electrons through the current collectors, and water is generated at the cathode side. So this is what happens inside a normally functioning proton exchange membrane fuel cell. But when there is a hydrogen crossover occurring inside the fuel cell, so this is where hydrogen pass through the from anode to the cathode side unintendedly, which results or leads to some implications in terms of the performance of the fuel cell. And this happened for a couple of reasons. So first is because of the porous nature of the membrane. Also, if there are defects occurring inside the proton exchange membrane, particularly the pinholes, cracks, and other defects. Materials integrity and degradation. Assembly, if the MEA or the membrane electrode assembly is not well secured. Operating conditions such as temperature, relative humidity, and pressure also contribute to the hydrogen crossover and concentration gradient. And there are a couple of implications of the HCO. So one of those is the fuel cell efficiency reduction, wherein there is a reduction in the available fuel at the anode side of the fuel cell. So also heat generation when there is an inefficient electrochemical reactions, which increase heat generation leading to thermal management issues due to localized heat accumulation. And when there is membrane deterioration, when HCO or hydrogen crossover promotes the generation of free radicals, which are responsible for PEM chains and catalyst attack, leading to formation of pinholes, cracks, and other defects. And when this also consequently result to mixed potentials, wherein there are local cells with unintended reactions that compete against ORR, leading to electrode polarization and voltage loss. So this work is intended to study the degradability of the PMFC performance given by their open circuit voltage or OCV values as affected by the hydrogen crossover. And the effect of HCO on OCV decay is not straightforward as it may seem. For example, Basha and Karan in 2023 found out that not all crossover hydrogen is fully oxidized, in contrast to the general understanding that hydrogen reacts with oxygen at the cathode side instantaneously. Hence, this also necessitates the development of a more sophisticated model to account for the increased systemic complexity, such as illustrated in their work. Prognostic methods of determining the effect of hydrogen crossover on the fuel cell performance are gaining much attention recently due to its low cost and high efficiency in modeling physical systems, including the first principle modeling and or equation-based modeling and the data-based modeling approaches. Fully theoretical modeling approaches rely on various parameters, and the development of a universally applicable model is mathematically challenging, provided that all relevant phenomena must be considered to accurately predict the OCV decay against a set of predictors, for example, HCO in this case. And since these models are complex, oftentimes assumptions and simplifications are applied to rule out the majority of the model complexity. However, this may not hold true realistically in most cases, as they are subject to researchers' perspective, which introduce some bias and could be responsible for the discrepancies between the predicted and the actual values of the OCV. Ultimately, larger computational resources are prerequisite to implement such simulation attempts. Whereas for database modeling, so they are highly accurate and optimizable. So these models resolve the challenges of the trial and error experimentation as they allow rapid optimization and prediction tasks. In terms of dealing with multiple variables, ML models can capture complex nonlinear behavior in a particular dataset that conventional fully theoretical models may struggle to carry out. Also, they are more adaptable to the introduction of new data sets and are scalable to handle big data. But one skepticism towards ML models or the data-based modeling approaches is that it may lack interpretability and their results might not directly translate to physical phenomena occurring inside the fuel cell. However, using algorithms such as, or to explain the ML models through measures such as Shapley values can help in determining how predictors influence the variability of the performance and durability of PEMFC. While experimental methods introduce valuable insights about the effect of hydrogen crossover on the fuel cell performance, some limitations of these approaches exist. For example, the effect of the presence of the contaminants, which could be extremely difficult to characterize experimentally. Also, the effect of varying operating parameters could present huge variation in their values, and the effect of cell assembly could significantly affect the measured hydrogen crossover, but most of the reported studies do not consider the implication of this instance in their characterization. Thus, machine learning is we believe one of the most advanced and intelligent optimization approaches currently available, especially in the application, in any scientific application, and also in specifically in the application for the fuel cell performance performance optimization and characterization. So machine learning involves the development and study of statistical algorithms that can learn from data and generalize the unseen data without explicit instruction. So ML empowers the deeper understanding of a scientific system by capturing complex, nonlinear patterns about it that a conventional modeling approach may struggle to carry out. Also, they act as surrogate models, which reduces both cost and time and practically suitable for optimization and predictive tasks when usefulness is prioritized over interpretability. So this work, because of those motivations, this work aims to study the PMFC performance degradation as influenced by temporal hydrogen crossover by developing machine learning model to evaluate the model based on its performance, fit results, correlation, and statistical validation to interpret the model predictions through Shapley values and to validate the reliability of the model on new unseen data. So for the methodology, so this is the modeling framework used in this work. It starts with the database construction wherein temporal hydrogen crossover current and OCVTK data are collected. So they are next pre-processed via conducting exploratory data analysis, handle outliers, and impute missing values. And then side by side, GPR model development, model evaluation, validation, and interpretation have been carried out. And then lastly is the model was deployed to check their prediction performance and evaluate their results. So for the data sets, the OCB decay against temporal hydrogen crossover data was adopted from Yao et al. 2024, which was used to train, test, and validate the GPR model generated in this work. So time and hydrogen crossover are the predictors, whereas OCV is the response variable in the data sets. So the data set has been divided and split into training data, which comprise 60% of the total data set, validation data 20%, and test data 20%. So random sampling was employed in the selection of the data or data points for training, testing, and validation sets. So for the GPR algorithm or the Process Regression algorithm, so this model um, is a non-parametric multivariate probabilistic model based on Bayesian inference to predict not only the mean of the unseen data, but also the uncertainty variance for each prediction. So each prediction not only gives the actual prediction, but also a distribution or a set of values for that specific data points that the model has predicted. So this model follows a general linear regression model with Gaussian noise given by equation number one, wherein epsilon is the Gaussian noise, h of x is the transpose vector form of the basis function. So what basis function does is it transforms the input values or input parameters to a higher dimension, wherein beta is the vector of basis function coefficients, and f of x is the zero mean Gaussian process with covariance kernel function k of x prime given by equation number two. So epsilon follows a normal distribution as a function of mean and error variance, wherein mean is assumed to be zero, and this relationship is given by equation number three. So overall, GPR is a probabilistic model where response can be estimated using the conditional probability of yi given f of x, I, and xi for a normally distributed function provided by equation number four. So equation number four can also be transformed to equation to its vector form, as shown in equations 5 to 6, wherein equation 5 is the vector form of the equation 4, and equation 6 gives the vector values for the coefficients of or needed for the equation 5. And where covariance function is given by equation number 7. So what covariance function or kernel function does is it transforms the prior to a higher dimension space to predict the posterior of the GPR model. So for the GPR hyperparameters, so hyperparameters control the learning process and influence the model's architecture and behavior. And in this case, the hyperparameters used in the GPR model development in this work are summarized in table one with their corresponding values and brief descriptions. So specifically for the kernel function, so this work used the Matern 5-2 covariance function, which is a generalized form of the radial basis function kernel with v is equal to 5 over 2. So that means it's twice differentiable functions that is less smooth than RBF, but more suitable in moderately smooth trends, such as that observed in the dataset used in this work. So the general form of the Matern 5-2 covariance function is given by equation 8, wherein sigma f is the signal standard deviation. Sigma L is the characteristic length, and R is the Euclidean distance between xi and xj, as shown in equation number 9. So for the model evaluation, so this work used the goodness of fit and correlation characterized by the coefficient of determination and correlation coefficient respectively. Also, in terms of statistical validation, so theta's results confirm if statistically significant difference exists between the model and experimental OCV values. So other statistical parameters such as standard deviation and variance values were also calculated to inspect the spread of the data points for both the model and experimental data sets. But ultimately, the goal of the modeling of the model training is to minimize the mean squared error or MSE given by equation number 10, which is common for any regression problem that use machine learning algorithms to solve optimization and prediction tasks. So for the model interpretability, the analysis of global and local Shapley values enables the understanding of the model prediction in relation to the physical phenomena occurring during the fuel cell degradation. So the Shapley value is a concept from cooperative gain theory used to fairly distribute the total gains or costs among a group of players who have collaborated. And Shapley values account for the effect of each predictor to the variability of the response variable for each prediction. So specifically, higher magnitude of Shapley values corresponds to greater influence of a predictor to the response. So meaning if the Shapley values or the numerical value of the Shapley value is high, so that means it contributes more, or that specific predictor contributes more to the variability of the response. And the sign of a Shapley value tells if the variable positively or negatively influences the response. Around zero Shapley value, a predictor is observed to exhibit no influence on the variability of the response. For the model development, the performance of the developed GPR-based model was evaluated using a new dataset of experimental data that was not used during the training and testing processes. For the results, the developed GPR model demonstrated exceptional predictive capability across all datasets. As shown in the tables, the RMSE values were in the orders of 10 raised to negative 5 with R squared and correlation coefficient of 1, indicating an almost perfect agreement between predictive and capable and experimental OCV values. So figure 2 illustrates that the predicted curve closely follows the measured OCV across the entire time range with a very narrow 95% confidence interval reflecting low model uncertainty. And this also was confirmed in figure 3 with all data points aligning along the 1:1 correlation line, indicating minimal deviation between predicted and actual values in both training and validation phases. So to interpret the model, global Shapley value analysis was performed. Figure 4 shows that both hydrogen crossover rate and operating time are significant predictors of OCB, with hydrogen crossover exhibiting slightly higher overall contribution. Figure 5 represents the distribution of Shapley values, which reveals that both variables exert positive and negative influences depending on the operational stage. This variability also suggests a complex, nonlinear interaction between hydrogen crossover and time in determining voltage decay. So the Shapley dependence plot in figure 6 identifies clear degradation phases. First, OCV remains relatively stable until approximately 35,000 hours, and then it also exhibits accelerated decline between 40,000 and 60,000 hours, and then experience the steepest losses beyond 70,000 hours. Local Shapley analysis in Figure 7 provides case-specific insights. At 0 hours, both predictors have negligible influence. At midlife, around 25,000 to 45,000 hours, time begins to impose a negative effect, while hydrogen crossover remains relatively minor. And in the late stage, beyond 70,000 hours, both factors contribute strongly to voltage loss, with hydrogen crossover emerging as the dominant driver. Overall, The GPR model achieved a high level of accuracy while providing physical consistent interpretations of PMFC degradation behavior. The integration of Shapley analysis not only quantified the relative influence of hydrogen crossover and time, but also revealed their dynamic contributions across different operational stages. So in conclusion, the GPR-based model was successfully developed to predict OCV values influenced by temporal hydrogen crossover with high accuracy and minimal uncertainty. The model showed excellent performance metrics during the deployment, including RMSE, R squared, and R values of 6.78 raised to raised to negative 5, 1, and 1 respectively. And that Shapley values indicate that both hydrogen crossover and time significantly influence OCV values with OCV or with HCO consistently dominating over time. Despite the general understanding that HCO deteriorates OCV, Shapley values or Shapley summaries showed positive influence, which was later contrasted by Shapley dependence, indicating negative impacts. And the local inspection revealed weak evidence of predictor influence on OCV between 40,000 to 60,000 hours, suggesting that other factors like membrane shortening resistance might be predominant. At the near end of the AES program, both time and HCO exhibited great influence on the OCV decay, wherein HCO predominated. So for future directions, one of the things that could be added to this study to extend this work is to incorporate other parameters such as design and operational variables. Also, to train beyond the current period of operation and generate model for various fuel PMFC designs, and to implement the model in monitoring systems for live performance tracking. So that will be all. Thank you so much for listening.